All right. So now we got section 4.5. I know some of you are looking at section 4.5 and you see linearization and Newton's method and you're like, Newton's method. We're not actually going to do Newton's method. It's just something that's not on the AP test. However, linearization is, so we're going to focus on that. Before we get to linearization, I do want you guys to look at this exploration 1 on page 233. Probably take you about 8 minutes. Hint for number 2, differentiate f of x and evaluate f prime of x at x equals 0 if there's a value because you didn't divide by 0. Then you have shown algebraically that f is differentiable at x equals 0. So at this point, I'll put this up on the dot cam. You can pause and then come back. And now that we're back, you can see that on my, whoopsies. There we go. I thought I had the function written up here already. My bad. So I've got I told you I had it written up there. So I've got f of x is equal to the quantity of x squared plus 0.0001 to the 1/4 power plus 0.9. I believe I copied that correctly out of the book. Indeed, I did. So you can see in my calculator, I actually have the function already typed into y1. If I go into my zoom menu, I can see zoom decimal is option 4. Zoom into the decimal, and it looks like on number 1, it is asking what kind of behavior does it look like you have at 0, 1, and it looks like a cusp. That is exactly what a cusp should look like on a function. Now, in order to show that there is not actually a cusp there, what we have to do is we have to find the derivative at that point, so at x equals 0. So f prime of x is going to be equal to power rule for the outside, 1/4 quantity x squared plus 0.0001 to the 1/4 minus 1 gives us -3/4 power times derivative of the inside. So inside it's 2x. That 0.001 cancels out, and so does the 0.9. Now we're finding f prime of 0, which would be equal to, let's see, let's simplify this a little bit. The 2 and the 4 become 2 in the denominator. So we have just x over 2 times the quantity of 0 squared plus 0.0001 to the 3/4 power. Oops, not x up top, 0 up top. We want to plug in 0 for x. Oopsies. Now we look at the denominator. I don't know what 0 plus 0.0001 to the 3/4 power is, but I know it's not 0. So 2 times not 0 is also not 0. 0 divided by not 0 is 0. It looks like my slope is 0. I want to find out the equation of the tangent line through the point 1 or 0, 1. So I know from experience that I've got this equation, y equals m times quantity of x minus x1 plus y1. We're looking at all of this activity up top. I've got my slope is 0 times quantity of x minus 0 plus 1. It looks like 0 times x minus 0 is 0. Plus 1 gives me 1. It looks like the tangent line here is just y equals 1. I know that on the calculator, or on the activity, it did not ask you to find out what, it didn't ask you to graph the tangent line, but I know that's going to help me out, so I'm just going to do it. I thought I was going to do it. There we go. In y2, I'm going to just graph my tangent line. Again, looking at my zoom, I can see, hey, that looks like a tangent line where there shouldn't be a tangent line. Now number 3 is asking me to zoom in repeatedly. Zoom in on that point. All right, zoom in. Okay, still looks cuspy. Zoom in again. Oh, it's rounding out a little bit. Look at that. Zoom in again. Ooh, look at that. It's almost looking parabola-y. Zoom in again. Oh man, that's widening. Zoom in again. I think you guys should know what's happening here from last chapter. We know that this function, in order to be differentiable, which we just showed on the flip chart, it has to be locally linear. So as we zoom in, it's going to become a line. Now, if we zoom in far enough, we should note that the line that it looks like actually matches the line that we just graphed. And the line that we just graphed is called the tangent line. So we can see if we zoom in sufficiently, the function looks like the tangent line. So the local linearization looks exactly like the tangent line, which leads us directly into what we're trying to do today, which is linearization. So let's go over here. There we go. There's a nice picture to promote linearization. It's trying to show what we just had in that activity. Notice here we have our tangent line close to the point of tangency, or what we call the center of the linearization. We have the line matches the curve for that brief moment around the point of tangency. Now, the thing that stinks is you do have to be really close to that point of tangency. Now, down here, to set up the equation, we actually have a couple of different declarations. We're starting with that point slope form of the line, or if you want to, you can start with my form of the line. Doesn't really matter to me. And then we go over here and we just plug in some different values. Instead of calling x1, x1, we call it the point A. And now we refer to the point A as the center of the linearization, or the center of the approximation, I guess we should say. That would make y1 equal to f of A, and the slope equal to f prime of A. Doing some substitutions in there, we now have the equation of the line is equal to f prime of A times the quantity of x minus A plus f of A. Doing some rearranging of stuff and calling this L of x being the linearization of the function. So that's why we use L. And we just toss this f of A out front. We develop a new formula. L of x is equal to f of A plus f prime of A times x minus A. All right, so that is the linearization of a function, which is summarized right here. Make this a little bit bigger so you guys can read it on your tiny screens at home. If f is differentiable at x equals a, then the equation of the tangent line, L of x, is equal to f of a plus f prime of a times quantity of f. L of x is equal to f of a plus f prime of a times quantity of x minus a. Sorry, I lost my train of thought there. Defines the linearization of f at a. The approximation f of x is approximately L of x is the standard linear approximation of f at a. The point x equals a is the center of approximation. You can, if you want to, memorize this formula right here. Or if you don't like doing that, just understand linearization and equation of tangent line are synonymous with each other. So you can use any formula you like to find the linearization of a function. Now let's get into a why would we want to do this. Here's an example of why we might want to do this. Let's say we want to approximate cosine of 1.75 without using a calculator. Now what we could do, we could produce the linearization of cosine of x at x equals pi over 2. Why would we use pi over 2? Well, first of all, pi over 2 is going to be on the unit circle. Second of all, if I was to take out my calculator, hey, there it is right there. I can go in here and I can find out that pi over 2 is equal to 1.57, which is close to 1.75, right? It's not dead on, but it's pretty close. So now going back here, again, my whole goal is to be able to calculate cosine of 1.75 without a calculator. So what I'm doing, I am producing that linearization to use that formula. L of x is equal to f of a plus f prime of a times the quantity of x minus a. To find this out, I need to find three things. A is equal to pi over 2. That's where we're approximating. F of a is equal to cosine of whatever a was, pi over 2. Cosine of pi over 2, well, here's where you might have to use your unit circle for it. Pi over 2 is right up here, so 0, 1. Looking at that, cosine is the x value, so it looks like cosine of pi over 2 is equal to 0. F prime of a is going to be equal to the derivative of cosine, so sine evaluated at x equals a. So really the answer is just sine of pi over 2. Wait a second. No, it's not. It's negative sine of x. Oopsies, I forgot my sine issue there. So the derivative of cosine is negative sine at x equals pi over 2 would actually give me sine of pi over 2 is 1, so this would be negative 1. I can now find out that my linearization, my L of x, is going to be equal to, and I'm just plugging stuff in here, f of a, 0 plus f prime of a, negative 1 times the quantity of x minus pi over 2. There we go. If I want to clean this up just a slight smidge, I can say that this is the opposite of x minus pi over 2, right? And why would that be helpful? Well, that becomes helpful because f of 1.75 is going to be approximately L of 1.75. So now cosine of 1.75 is approximately equal to negative 1.75 minus pi over 2. Well, pi over 2, again, was just that 1.57. So if I was to take away 1.57 here, I know the answer is going to be negative, let's see, become 15, knock that off, we get 8. Negative 0.18 is what I'm guessing cosine of 1.75 is. Now, just to show you that I know slightly what I'm talking about here, I can find out that cosine of 1.75, oopsies, cosine of 1.75, look at that. Pretty dead on. It's negative 0.178. I was, 2 thousandths off without touching a calculator on that. And even further, I could actually go and look at the cosine of 1.75 and my approximation of negative 1.75 minus pi over 2. I can actually find out I was even closer than I thought. If I used an actual value of pi over 2, I could have it at negative 0.17920367232. So here, I could actually find out my percent error. If I want to find out my percent error, and some of you have taken Algebra 2, so my error, not Algebra 2, like math, not math, science classes where you actually have to calculate percent error. I'm sorry, I'm having a rough time talking right now. So to find your error, all we have to do is find the difference between our actual answer, our approximation, and the actual answer. So our error is going to be equal to the magnitude of f of 1.75 minus L of 1.75. So that error, again, just looking over right Chahira, I'm gonna add that minus that. All right, so it looks like 9.57 times 10, 9.9, 9.576 times 10 to the negative fourth. Approximately 9.576 times 10 to the negative fourth. So what I can actually see here is this is actually accurate within 10 to the negative third, which is pretty impressive. We're pretty darn close. And 10 to the negative third, 3 decimal places. Hey, I'm pretty dead on there, right? So that's pretty cool. Let's look at some other stuff that we can do here. This one. You guys might want to try this one out. Try to make a linearization of f of x is equal to the square root of 1 plus x at a equals 8. Maybe pause it. When you unpause, I can give you some hints here. We're already given a. You can find f of a. Given the f of a, it's pretty clear why we chose a equals 8. F of a would be the square root of 1 plus 8. We're trying to find values that it's easy to calculate for. So square root of 1 plus 8 would be square root of 9. Just 3. Maybe pause, try to find f prime of a, and then come back. So f prime of a, looking at that, the derivative of square root of 1 plus x. Well, again, I'm talking about square roots. So I know the derivative of square root is 1 over 2 root the stuff times the derivative of the stuff. The derivative of the stuff here is going to be 1. So 1 over 2 root 1 plus x evaluated at x equals a. This ends up being f prime of a is equal to 1 over 2 root 1 plus 8. So 1 over 2 times 3, 1/6. And now we can find the linearization. So our L of x is going to be equal to f of a, 3 plus m 1/6 times the quantity of x minus a. There we go. There's our linearization. Now all this stuff over here, what I'm trying to show you is the difference in the function value versus the linearization value. So the easiest way to do this is probably just to bust out your calculator. And what I would probably do here is just go into my always forget to turn the calculator back to calculator. There we go. So go into my y equals menu, type in the function for y1. So the function was the square root of 1 plus x. The y2 would be our linearization, so it would be that 3 plus 1/6 times the quantity of x minus 8. And now I can go into my table of values and find out how close my approximation is, like at 7.9. The square root of 1 plus 7.9, or the square root of 8.9, is 2.9833. Look at that. Dead on value, pretty darned close to the approximation. Blue and dead on, red and approximation. Show you even closer how, or show you even better how close it is. Absolute value of y1 minus y2. Again, going back up here, it's accurate within 4.7 times 10 to the negative fourth. So 10 to the negative fifth. It's accurate within 10 to the negative fourth there. Looking further, I know I also wanted to test at 7.99. Look at that. Accurate within 10 to the negative sixth. My goodness, that is so accurate. Then watch this. 8. The error there is nothing. Any wild idea there? I'll just ruin it for you. The center will always yield the approximation is dead on to the function value. So that's where your approximation won't be an approximation. It'll be completely accurate. If I plug in 8.01, look at this. Again, accurate within 10 to the negative sixth, 8.1. What you should be noticing here is as we go away from 8, we're getting worse and worse approximations. When I finally get far away from 8, look how bad my approximation is. I'm off by almost a half, and that's just not good. Way not good. All right, let's see here. I think I have a nice little graph to show you that as we zoom away, this error between the linearization and the curve becomes bigger and bigger. Linearizations for the following functions near 0. These can be helpful if we're ever trying to evaluate functions. Just ruining them for you. There's the linearizations. 1 plus x to the kth power is basically 1 plus k x. Sine of x is basically equal to x. Cosine of x is basically equal to 1. Tangent of x is basically equal to x. So like just to show you some things that you could do with this, using a linearization for like, let's say 1.01 cubed. If I wanted to find out approximately what 1.01 cubed is, well, that is going to be approximately in this format, where my x value is 0.01. My k value is still 3. So now this is going to be approximately 1 plus my k value of 3 times 0.01. So just doing this in my head, 1.01 cubed is approximately 1.03. And just to show you that I'm not crazy here, look at that, 1.03. If I wanted to do, let's see, the square root of 1.0001, I don't know what the square root of 1.001 is, but I know 1.0001 is 1 plus 0.0001 to the half power. So this is going to be approximately, using this approximation over here, 1 plus k 1/2 times 0.0001. Well, half of 0.0001 is 0.00005. So this would be approximately 1.00005. And just looking at what the square root of 1.0001 is, square root of 1. Square root of 1.0001. Look at that. 1.00004999999. It's pretty darn close, right? Pretty darn accurate. Again, the main important thing here is it's only going to be accurate when you're close to the center. So here, you probably wouldn't want to do like 2 cubed to approximate this. That'd be too far. And so, oh my goodness, square root of 51 or the cube root of 60. So let's look at this, something that we could do here. Let's just do this first one here. This first one, basically what I'm trying to do is I'm trying to approximate what is a square root. So let's call our function the square root of x. My x value, I'm trying to find the square root of 51. I look for a square, a perfect square that's close to 51. So that's the a value I'm going to use. My a value, close to 51, that's a perfect square. That's a 49, all right? So here, my f of a is going to be 7. My f prime of a is going to be 1 over 2 square root of x, evaluated at x equals 49, which would be 1 square root of 49, 7 times 2, 1/14. So I now know that my linearization L of x is going to be equal to f of a, 7 plus f prime of a, 1/14, times the quantity of x minus a, which was 49. So now bear with me for a second here. The square root of 51, going back up here, is going to be equal to f of 51. From this section, I know that that's approximately L of 51, which would be equal to 7 plus 1/14 times the quantity of 51 minus 49. Well, 51 minus 49, I believe that's 2. 2 times 1/14 is 1/7. So the square root of 51 is approximately 7 1/7. I know I've told some of you that I hate mixed numbers. If I haven't told you that, I do hate mixed numbers. So just because I want to know what 7 1/7 is, I'm going to get in touch with my calculator, and even further, I want to know what the square root of 51 is. 7 1/7, 7.143. Square root of 51. Square root of 51. 7.141. Hey, that's pretty close, isn't it? So again, finding a linearization close to the center produces, or finding a linearization as long as you're close to the center produces an approximate value. Again, these are approximations, so if you're not the approximatey kind of person, this would suck. If I wanted to do number 2 here, I would find out that my f of x is equal to the cube root of x, or x to the 1/3 power. My a value, if you don't know perfect cubes, 1, 8, 27, 64 is a perfect cube. F of a would be the cube root of 64, which is 4. F prime of a would be equal to the derivative of x to the 1/3, so 1/3 x to the negative 2/3 power, evaluated at x equals 64, which would be equal to 1/3 times 64 to the 2/3 power. 64 to the 2/3 power, and I might be doing too much stuff in my head. If you need to use a calculator, you can. I see 64 to the 1/3 power would be 4. Squared would give me 16. 16 times 3, 32, 48. So this would be equal to 1/48. Whew. So my linearization would be equal to my f of a, my 4, plus my f prime of a, 1/48, times the quantity of x minus my a, 64. So therefore, my cube root of 60 would be equal to f of 60, which would be approximately equal to L of 60, which would be equal to 4 plus 1/48 times the quantity of 60 minus 64. So this would be 4 plus 1/48 times negative 4. 48 divided by 4 gives me 12. So this would be equal to 4 minus 1/12, or 3 11/12. And just to show you that I think I know what I'm talking about here, I can go in, I can do 3 11/12 and the 4th root of 60. Oh, pretty close, pretty close. right. Turn off the calculator. Let's go back to finish this up. All right. One last thing for us, differentials. You use differentials to calculate approximate changes in functions. They look super confusing. They are not. A differential is just referring to this whole concept of dx right over here. So as long as dx is small, the change in y, we would call dy, is approximately f prime of x times dx. And the way that we get that is just looking over here. If I was finding f prime of x is equal to dy dx, again, just those are the same meaning. They just have different symbols. If I multiply by dx, I get f prime of x dx is equal to dy. So really what we're trying to approximate here is a tiny change in y based off of a change in x. And there's some pictures that I can show you to try to illustrate that. But really, if I want to find dy for the given value of x and dx, all I'm going to do for like this first one, right over Chihira, my dy is going to be equal to f prime, so 5x to the fourth plus 2 dx. Excuse me. To evaluate at the given values, I'm going to find out that my dy, my change in y, is going to be approximately 5 times 1 to the fourth power plus 2 times 0.01. So looking at that, I would actually find 5 times 1 to the fourth. So 5 plus 2, 7 times 0.01. That would be 0.07. This is approximating the change in y from x equals 1 to x equals 1 plus 0.01. So this is approximating delta y, which would be f of 1 plus 0.01 minus f of 1. Which in this case, if I'm looking at trying to figure out what the value is there, to compare the approximation to the exact value, I can grab my calculator, plug in the original function, being x to the fifth plus 2x, nope, x to the fifth plus 2x. The actual change would have been f of 1.01 minus f of 1, which 0.071. I mean, it's pretty close. I'm trying to figure out how much does the function change given a change in x. So one way to do that is by using your differential. The other way, which would be more accurate, would be finding your new function value, subtracting off your old function value. This one's going to be even easier to calculate. My dy is going to be equal to derivative of sine of 2x is going to be cosine of 2x times my chain of 2 times dx. So the change in sine of 2x from pi to pi plus 0.01 is going to be approximately dy equals 2 cosine of 2 pi times 0.01. Cosine of 2 pi is 1. So 2 times 1 times 0.001 is going to be 0.02. And again, to find the change, the actual change, the delta y is going to be equal to f of pi plus dy minus f of pi. And the only way that I can think of to get an accurate answer on that is going up to my calculator. Move it out of the way so I can see a little bit better. Here I'm going to go into my y equals menu, plug in the original function, sine of 2x, on the home screen, y1 of pi plus 0.01 minus y1 of pi. Of pi. We can see 0.01999999, which is pretty darn close to the 0.02 that we estimated without having to touch our calculator. And again, our whole idea is to not touch our calculator. If you want to see a nice little illustration of what the dy is doing, let's not here, that's just filling it out. So you can see here's a nice illustration. The dy is the approximate change between two points. Ooh, oh man, okay. Let me see if I can remember a different type of, well, let's look at this problem. The radius of a circle increases from r equals 5 meters to 5.1 meters. Use dA to estimate the increase in the circle's area. So what we have to do here is we have to start with an area formula for a circle, right? So we've got A is equal to pi r squared, right? So if we have A equals pi r squared, what we are trying to figure out here, we are trying to start from r equals 5 meters, and we are trying to increase our r. Looking here, we're going from 5 meters to 5.1 meters. How far are we trying to increase our radius? We're trying to increase it 0.1 meters, right? So in order to approximate this, the approximate increase in the area of this circle is going to be dA is equal to the derivative of pi r squared, well, we're differentiating with respect to r, so it would be 2 pi r times dr. The approximate increase in the area here is going to be change in area. In this situation is going to be, let's see, the 2 pi times the radius of 5 meters times the dr of 0.1 meters. So looking at this, 2 times 5, that would be 10. 10 times 0.1 would be just 1 times pi. Gives us an increase in pi square meters. So what we're saying here is we think that the area of the circle is going to increase by pi square meters. So we can actually look at that by finding the delta area. Delta area would be the pi bigger radius squared minus pi smaller radius squared. And I really can't do that by hand because I don't feel like doing what 5.1 squared is. So I have to grab my calculator and do pi times 5.1 squared minus 5 times 5.1 squared minus pi times 5 squared. Look at that, 3.173. Pretty close to pi, right? That's pretty cool. So we can only do this, though, when the radius increases slightly. And if you guys are good tomorrow, maybe I'll show you another cool thing that we can prove. using this type of situation. But before we get there, let's look at, that's the cool thing. I don't want to do that yet. So there's your suggested assignment, and I will see you guys tomorrow.